Hello everyone, this is the video lecture for Calculus 2, section 11.10, Taylor series. Super awesome. Let me give you the formula here, and we will go from there. I have f of x is equal to summation n equals 0 to infinity of f to the nth derivative at c divided by n factorial times x minus c all to the n power. Well, there's your formula. Awesome, right? Uh, Let me write this out a couple times. So basically, we're going to have f of c plus f prime of c. This is what I'm going to do instead. My notes have that, but I want something else. F prime at c divided by 1 factorial times x minus c to the 1. And then I got f double prime at c divided by 2 factorial. So that's a prime. That's a 1 and a 1. But this here is now a 2. And then triple prime, 3 x minus c cubed, and so on and so forth and stuff like that. Okay, cool. So there's a formula for all this, I guess you can say. And so what are we doing? Why are we doing all this? What's this huge formula even mean and all that kind of stuff? I'm taking some kind of transcendental. Let me see if I can even spell that. Transcendental. Nothing to do with classic literature, by the way. Transcendental functions, and we're converting them into polynomials. This is pretty neat stuff here, actually. Imagine for a second here that we had a sine x, and somehow we can rewrite that as, I'm just making something up here, 1 plus x squared plus x to the 4th plus x to the 6th plus da-da-da-da-da. And so the sine wave looks like this, right? And I guess over here. And what we're doing is saying, you know what? Right here, it has this feel like it kind of has this cubic feel to it right here, you know? So maybe I can approximate it with x cubed. Or if I keep going, I'm like, you know what? This right here looks like it's going to be an awesome little function. Notice that it's approximating this sine wave for a lot longer. That looks like it's a cube, but I'm going to make it an odd, I don't know, negative x to the 5th, something similar to that. And you're like, you know what? I bet I can go even further. And so I can make all of this here. And there we go. Now that is some kind of x to the 7th or something like that. I'm just making stuff up. But my idea is that this sine wave could be approximated for some interval. And that's super awesome. So why is that super awesome? Well, derivatives of transcendentals are sometimes okay. What's a derivative of sine is cosine. That's easy. But derivatives and integrals of polynomials are super nice because, I mean, they're very easy to do that. So there is a strength here because what if I just don't have this? What if I have an ln? What if I have an arctangent? I don't know. So, I mean, all these transcendental things, e to the x, all this stuff, yes, there's derivatives, and yeah, we know most of them, and it's not too bad most of the time. But, like, what, integrate all those guys, and all of a sudden I'm start freaking out. Well, you can derivative or derive or integrate this polynomial stuff, like, super easy comparatively. Okay. Phew. So that's the point. I have one last little note here, is that whenever you see the word Maclaurin, what they're trying to imply is c equals 0. If they say the word Taylor, then c is some other number, they have to give it to you, okay? So one of the problems might say, blah, 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 the Maclaurin series. And they won't tell you what c is because c equals 0. That's just what Maclaurin is. Taylor says, oh, well, you know, Taylor series, c equals 2 or something, and then you go from there. Phew. One last thing. I know that was the last thing, but now there's one more last thing. There's a page, like a sheet in the formula book, and it has a whole bunch of formulas and stuff for this. And one of them in particular is that sine that we had just talked about here. So, like, this is completely wrong. Where did I have it? Yeah, this stuff here. That was completely wrong. It's actually this right here. And yeah, and then it keeps going forever and ever. So there's a formula sheet with a lot of these common transcendentals that are already translated into this kind of stuff. Look for this kind of thing somewhere. And then you got your cosines and you got your other things on there, e to the x and all this other stuff. This is a super helpful page to be having when I'm going through this, and I will reference it many times. All right, now let's finally get to some of these questions. So 003, this is a strange one. It has very little to do with what we're going to be doing for the rest of this section. But because it was strange, I needed to do it. So let's go ahead and do it. They say that the nth derivative at 0, that's Maclaurin, is equal to n plus 1 factorial. Okay. And so if that, then I have my summation, I'm sorry, f. Oops. Then my f of x is equal to summation n equals 0 to infinity of n plus 1 factorial over n factorial, and then x minus 0 to the n. Whatever. So something, I can't remember the exact format of this. This is one of those you can get it wrong 5 times, see what their answer is, type it back in. No randomization or nothing. But I wanted to talk about what's going on just a tiny bit. That's good enough. So I can split this guy up and cancel these guys. And so my answer, what they want on the inside here, is n plus 1 x to the n, and that's it. You're done. Move on. Next question. Oh, r equals 1, because this is geometric technically. Cool. So what was going on here is that they're trying to use this formula right here, and they say, well, just replace this guy with the n plus 1 factorial. That is literally all. Oh, and the c is equal to 0. So they just said, take this formula, replace this thing, replace that thing, and then simplify. And that's what I did. I replaced it right there, and then I blah, 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 and there you go. There's your answer. Next one. 11, 10, 0, 0, 1. We're going backwards, it seems. So this is the second to last section in Calculus 2. I do want to do Taylor series, and I will be using Taylor series, but also we need to know the strength of that little formula sheet and make good use of it, okay? So in the formula book, there's a big list of these things, and I see there's one for sine, and I wrote it out already, right here. I wrote it out already, but there's something else included at the end that I want to specify, so let me rewrite it one more time, and I'm going to show you how to use this little formula sheet thing. Okay, so it has this in the formula book on that page. It's near the end. But then here at the end, it also says, well, this is equal to the summation of n equals 0 to infinity of negative 1 to the n x to the 2n plus 1, and then all divided by 2n plus 1 factorial. Whew. This right here, this is all in one line in that formula book page thing. Okay, so this is what we're looking at in the booklet. And what I'm going to do is basically see this goes to this. I'm going to kind of forget about that right now because we don't really need that. The reason why is because it says, well, my answer is summation blah, 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 summation blah, blah, blah. So, like, you're basically just going to copy that and put it in. Basically, there is one small modification. Notice that what we have is pi over 2x, and what they have is just an x. So wherever you have an x, and there's only the one right there, what you're going to rewrite over here is pi over 2x. So here's your final answer without any math, which is nice. It's pi over 2x to the 2n plus 1 all over 2n plus 1 factorial. That, I'm not kidding you. That is exactly what you type in here, and you're done. Now, your radius of convergence is equal to infinity. You're going to have to type that because you can see that there's factorial in the bottom, and this is geometric, but this is factorial in the bottom, which is way stronger, and it's going to, I guess, it's going to converge always. That's it, always converge. But we've had that many times in the past sections. I don't want to go into that again. I have a little note that says, not every problem is this simple. But if it is this simple, please don't waste your time. Don't go through the whole process. I'm going to do the process here in the next problem. I will. And I'm going to do it again. But if there is a formula, just use the formula. It's real easy, okay? That's a good thing. Good thing. All right. So it says that my f of x is equal to x to the fourth minus 2x squared plus 3. And they say approximate this with c equals 2. And basically f of x is equal to what? All right. I mean, they don't have any summations. They don't have anything like that. They just say f of x equals what? This is a big note here in my notes here. I'll just read it to you. That way it's not biased at all, is it? Wow, this is a stupid problem. I wrote that. In WebAssign, try typing the original back in and see what happens. So my first suggestion is for you to take this and type this in. Now, I did not do this. The way I go through the homework is a slight bit different than how you do it. So I didn't actually attempt that. But I would say on this problem, just type this right here and see if it works. If it does, cool. You skip the problem. You don't have to talk about it. We're done. If it actually needs more, then we're going to go through it here. But why is it stupid? Not just because of that, but why is it stupid? It says, why stupid? Because we are taking polynomials and we're changing them into polynomials. So we are just making it more complicated for no reason. I have that's a verbatim statement. I don't know who wrote these notes. Oh yeah, it was me. So yeah, this has got to be the most pointless problem I've ever seen. But it is a good starting demo problem. And so I'm going to use this as a demo problem for the Taylor series stuff, okay? This is super easy, basic Taylor stuff that we're going to do. And so it says c equals 2. And so what I'm going to do is start with, this is what I'm going to do. I'm going to do this f of x stuff here. So we got f of x is x to the 4 minus 2x squared plus 3. And then I'm going to do f of 2, right? And I'm going to plug in 2, and guess what? I got an 11. Awesome. I'm just copying from my notes. Now I'm going to find the first derivative. So that's 4x cubed minus 4x plus 0. And so then I'm going to plug in f prime of 2. These are all very important here. Whenever I plug in a 2 into this guy, I get 24. Okay? Second derivative. So now I take the 3 and move it down. 12x squared minus the 4. Second derivative. Double derivative. Second derivative at 2, I plug it in, I'm going to get a 44. Third derivative, we're running out of Newtonian notation. 24x minus the 0 now. F triple prime at 2, so I'm taking a 2 and plugging it in there. Obviously, we get a 48. The fourth derivative, so this is where we change a little bit, because, I don't know, maybe Newton wasn't thinking ahead. I don't know. That was just a joke. I'm a Leibniz fan. Sorry. You're just going to have to deal with that. Newton's cool too, I guess. So, f to the fourth derivative at 2. I plug in a 2 here. Come on, plug in a 2. What do you get? Well, you get 24 because there's nowhere to plug in a 2. So, whatever. And then now, finally, your fifth derivative. What's your derivative of that? Is a 0. And so, you don't even have to do this. 0 and 0, 0, 0 all the way down. So basically, we don't need any of this. This is all the numbers that we're going to need. And now let's put it all together in a most complicated form. But again, this is a good demo problem, okay? So my f of x, final answer here, starts with literally the 11 plus. And then I take the 24 and I divide it by 1 factorial, x minus 2 to the 1 power. There's a pattern here. Next is the 44. So 44 divided by 2 factorial, x minus 2 squared. Keep going. I got my 48. 48 divided by 3 factorial x minus 2 cubed. And then I got my 24. 24 over 4 factorial x minus 2 to the 4th. And that is the answer. Now what I'm going to do is I'm going to simplify that down a little bit. So I did not simplify it a lot. 1 factorial is 1, 2 factorial is a 2, 3 factorial is a 6, and 4 factorial is actually a 24, so kind of funny how that works. 24 x minus 2, you don't need a 1 right there. That's going to be a 2, so it makes it 22, x minus 2 squared. That's going to be a 6. 48 divided by 6, I'm sure that's a thing. 8. I know I should have known that. Just, it's fine. 24 over 24 is a 1. 1, there you go. All to the 4th power. And because everything else would have been a 0 after that, 0, 0, 0, you don't really have to write those. This is the final answer. So this is equal to this. And that's awesome. Cool, man. That was so cool. Why? Radius of convergence is infinity, and I have because whatever. So, next question. You can see that some of these problems are not on my happy list. This one here is actually not too bad. They have f of x is equal to 3, 1 minus x to the negative 2, and they say Maclaurin. They say that. So then they're meaning that c equals 0. I'm going to do the exact same procedure as last time. I'm going to basically write out my originals, and then my derivatives and second derivatives and all that kind of stuff. And then I'm going to plug in a 0. So plugging in a 0 into this guy makes it turn into a 1 right here, and 3 times 1 is a 3. Okay. And now I take my first derivative. So again, the derivative means it comes out to the front. Leave the inside alone, minus 1 from the power, and then take the derivative of the inside. So technically this is a positive 6. When I plug in a 0, again, it's just going to be a 1. It doesn't really matter about negative powers and all that stuff, so I get a plain old positive 6 out of that. Again, this is a positive 6. Here, this is what I'm going to do. There you go. So now we're better. So now derivative of this guy, the negative 3 comes to the front. Whoa. 3 times 6 is 18. Now it's a negative 4, and again, derivative the inside. 2 negatives make a positive, though. Whenever I plug in my 0, I get 18. I mean, this is not terribly hard. It's just kind of repetitive. The 4, blah, blah, blah. We've already seen this. Okay, that's good enough. We're done. We're done with this. Okay, I don't really care anymore. So what I want to do is rewrite my big, long equation thing. So we start with a 3 right here, that 3. And then I say 6 divided by 1 factorial x minus the 0, Maclaurin, to the 1 power. And then I got 18, 2 factorial x minus 0 squared, 72, 3 factorial x minus 0 cubed. And we would keep going, but I'm done basically with that. So let me simplify it. We got a 6 here, x. I'll just say 6x is fine, because the zeros are going to cancel anyways. 18 divided by 2 is a 9x squared. Here we got, that's divided by a 6. Did I get a number for that? I think it's 12 x cubed. And again, it'll keep going forever and ever. Now, if you type this in with the ... dots, they still don't accept it, because what they want is you to convert this into a infinite series. So there's always a little trick in there, isn't there? Always a little trick. And that's okay. I mean, there's a pattern here. Uh-oh, did I say the B word? So there's a pattern in here, and we're going to try to grasp what that pattern is. Notice that it's 3, 6, 9, 12. What's the next number? Can you guess? It's 15. They're all 3s. They're all in terms of 3s. So I can actually say, like, I could factor a 3 out from every one of these guys. And so I'd have 3 times 1 plus 2x plus 3x squared plus 4x cubed and so on and so forth, right? And now you can even see a more distinct pattern. You're saying that this number here in the front is always one more than the one up at the power. And what we actually start with right here, if you notice, it's x to the 0, and this is a 1. So we're actually starting with x to the 0. So therefore, right here, you can see, starting with 0. So this is my n equals 0 term. And therefore, the number in the front is not n, rather, 3 times, it's n plus 1. And then x to the n. Again, plug in a 0. What are you going to get here? You're going to get a 1, and x to the 0 is a 1. Therefore, you get a 1, and everything's fine. Of course, you got to put the 3 in the front there to make it all work. But there you go. There's the answer. This is geometric right here. You can see that. Geometric, so therefore radius convergence is going to be a 1 because x is less than, or we'll just, absolute value of x is less than 1. So 1. There. All right, I think those are the harder ones. There's one more that's a little bit lengthy, but past this, I'm really going to try to use the formulas as much as possible. So e to the negative 2x is equal to the summation 0 to infinity, whatever. This has got to be the easiest one ever. If you look back at the formula book, we actually have e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Moving on like that, and it's equal to, it says the summation of x to the n over n factorial. And you can kind of see that pattern there anyways, so that was a good thing. So to make use of this formula here, what I'm going to say is, hey, you know what? They look very similar. We got this one instead of this one. That's the only difference. And so I guess you could say like your old x, wherever you had an x in particular right there, you're going to convert it to this negative 2x business. And that's the answer. You're done. Like, that's it. Negative 2x to the n divided by n factorial. That's it. Now, what's the radius of convergence? It's infinity. It always converges. The reason why is because the factorial in the bottom again. Geometric in the top, yes, but factorial is stronger if it's in the bottom. Radius convergence infinity always converges. Okay, awesome. Next problem. This is one of my more annoying problems. It's not terribly hard, and we're going to be using the formulas, but it just really is not my favorite. I don't like having to do these. So I'm sorry if I get a little bit on it. Okay, so this guy is equal to n equals 0, I think. To infinity, this one. Is it 0? Yeah, it's 0. This guy here is binomial. Binomial. And you can look this up on the little chart. I believe it's the last one, like at the very bottom. And it has this kind of format here. They might use a K or something to go through with the formula. And we're going to be doing that formula. And it's weird, but we can do this. So I have to rewrite this just a tiny, tiny bit in order for me to do this correctly, though. Okay, so first off, I want to... I need a 1 right here. That's the only difference that I need. So I need a 1 right there. And so what I did is I factored out a 4. I know this is a little weird and still kind of within the cube here. So within the cube, I'm factoring out a 4. So I'm left with now x over 4. Hold on. That's right. Okay. So he's still inside. This doesn't really make sense because it's more like this. But if you redistribute your 4, these cancel. You get a 4. So everything's fine so far. I want to pull the 4 out now so that it's on the outside. And so you have to cube it, obviously. And that makes my 64 now. Okay. And this is a little bit better for the formula. There's one last step, I guess. So we got 3 over 64, which I don't think cancels. And then we got 1 plus x to the 4th to the negative 3 power. This here is what I'm going to use with that formula. And just simply plugging it in then, I mean, this is just a copy-paste. We have negative 3n. That's the binomial part. Okay, so just hold up. That's not division. That's not division. Not division. Okay, that's the binomial part. Okay, we'll definitely do that here in a second. And then I have x over 4 to the n. Okay, so like from here to here is that formula. This is just me using that formula. I don't want to write it out anymore. This is fine. But we definitely need to talk about the binomial coefficient, I guess. So I'm going to only look at this binomial component off to the side, and I want to simplify it. And this is what it looks like. And I think that this is in the formula book as well. Regardless, just kind of follow along here. So negative 3, negative 4, negative 5, dot, 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 all the way until negative 3 minus n plus 1, all divided by n factorial. Okay, so this equals that. And what we need to do is kind of simplify it down a little bit. Notice that there's a whole ton of negatives, and so what you can do is pull out a negative from each one of them. And that's a lot. That's why it's negative 1 to the n power, not just negative 1. There's a whole ton of negatives, so 1, 2, 3, 4, a whole bunch of them get pulled out, n amount, leaving you now with 3 times 4 times 5, which honestly is so much easier. And here I'm going to do an n plus 2. So if you notice here, right here, they simplify one another to make just a plus 2. And that's a nice thing as well. All divided by n factorial. Okay. What I want to do now is I want to make this into a true factorial understanding. And what factorial is 1 times 2 times 3 times 4 all the way out, right? Well, we don't have the 1 and 2 in the top. And so in order to do that, I'm just going to add a 1 and a 2. And then I'll proceed on with the 3, the 4, the 5, and all the way to n plus 2. Yep, just verifying there. But if I do that to the top, this 1, 2 thing, I also need to do it to the bottom, right? Everything here is multiplied. Don't think it's like anything basic. You can just cancel those if you wanted to. So that now makes sense. This is now some kind of factorial business on the top, which is a lot easier to write. So that's n plus 2 factorial. And then I just got a 2. 1 times 2 is 2. And then an n factorial. Okay. I can now simplify that down. N plus 2, n plus 1, n factorial divided by 2 times n factorial. And those guys now cancel. Whew. And so, still got the 2 there. Negative 1 to the n all over 2. And then times n plus 2 times n plus 1. And this is that negative 3n business, that binomial component. What you do now is you go back to what the box is and how let's go way, way back. We're talking right here, right now. This is your answer. Okay, but I'm going to replace this part with what I just found, that little fraction action. And so here we go. Final answer, 3 over 64 times, and I got negative 1 to the n over 2, n plus 2, n plus 1. That's my binomial component. And then I got x over 4 to the n. Whew. And that is your final answer. This is geometric. Radius of convergence is 4. We did that a bazillion times by now. So there you go. Awesome. And we're done with that one. All right. Whew, man, I do not like the binomial stuff that much. I have 3 more problems. They're actually much faster. And one of them's a little weird. This guy here, I think, is pretty straightforward. Let's do it here. So I have 8 times the integral of e to the x minus 1. As in, I want to make sure we're understanding this here. This is e to the x minus 1, okay? So not all in the power, divided by 3x dx. And they say that this is equal to summation of n equals 0 to infinity. Oh, whoa, 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 whoa. I'm wrong. It's a 1 to infinity. As you know, with these past sections, this it's really important nowadays. Just saying. So this is equal to that, and now we got to solve it and stuff like that. Well, this right here, I have a formula for that, and this is going to look very strange, but it still works. That's my formula from that little sheet. And I want to start simplifying this a little bit. Like the x can come up, the 3, and all this kind of stuff. And my handwriting is really tiny here, so just kind of bear with me because I'm trying to make it all kind of together. Then minus 1 dx, I guess. Okay, so I took this and put it kind of on the inside. You can do that because this is technically a constant. The x is going to be a number, I don't know, 5 or 2 or -1. And therefore, it'll just be a constant on the inside of the summation. Therefore, it's okay to just put it on the inside. It just so happens that these x's here will cancel a little bit. Why did I put an 8 right here? Oh, I know what I did. There you go. Sorry. I always mess these little things up. I put the 8 inside as well. That'll be important for just in a couple minutes. So I've got 8/3. And then these x's right here, that's a 1, that's an n. So then technically x to the n minus 1 now. And this is still all divided by the n factorial in the bottom. And then still minus 1, and then still integrate. Whew. So now I actually integrate it, and it's not that hard. Remember that I'm just going to add 1 to the power and divide by the new power. And so we get 8/3, and then I have x to the n divided by n. Actually, it's n and then n factorial because this is still in denominator. It's not like you don't take a derivative with n though, so it's just kind of like a number right there. Yeah, it's so ugly. Let me start over. Grr. So add 1 to the power, divide by a new power. You still had an n factorial on the bottom. What's your integral of 1? X. And of course, when you integrate, you got to have a plus c. What's funny is, and I can't remember if it's going to be this or if this is your answer. This is what I have written up here, but this right here is what I have written there. I can't remember if there's an X in the beginning or not of this problem. I don't know. But this is your answer right there. It's not hard. Just kind of type it out and, well, you're done. Okay. 2 last problems. This is one of my favorites here because it's so short. And I like to do little tricks anyways. It says, find the limit as x goes to 0 of 1 minus cosine of 5x, all divided by 1 plus 5x, and then minus e to the 5x. Figure it out. What they're wanting you to do is find out like a infinite summation series thingy for each one of these or something. I'm not getting into all that. I mean, come on, we're near the end. So you know what we're going to do? You're going to plug in a really small number. Let's just plug in x equals 0,001, something like that. And what I got whenever I plugged it in, I just plugged it in, and I got negative 0.999833. What do you think your answer is? What are you going to put in the answer box? -1. Very good. Good job. So you don't have to do this one. I wouldn't. It's not enough time. Just put it in, get the answer, moving on, okay? I know, I'm cheating, whatever. So last problem, I got summation n equals 0 to infinity of -1 to the n times 2 to the n x to the 8n, all divided by n factorial. And they say this is equal to what? And what we're trying to do here is we're going backwards, where we have a summation and they want like a plain old f of x kind of thing. So they just want a plain old function. So what I did is I said, n power, n power, n power. I have a whole lot of n's, all to the n power. and then an n factorial on the bottom. You know what this kind of looks like? It kind of looks like summation x to the n over n factorial. It's just that I have a more complicated x. And so that's exactly right. And what is this equal to is e to the x. So I'm going to say that this guy right here, like equals, is e to the negative 2x to the 8th. And like that is it. You're done. We're done with that section. All right. Thank you very much. Have a great day.